Okay, hello. My name is Chinmay Nurke. I am teaching the CSE 534 Quantum Information and Computation course this autumn at the University of Washington. This lecture is the lecture zero for the course. What it is basically a simple, broad perspective on the field of quantum computation and the administrative notes for our course, so that when we meet in person for the first time in a couple weeks, you we can just get right ahead uh, into some of the mathematics and really start digging into this field in earnest. That being said, this informational video is very light. It's very simple. There's no equations, there's no mathematics. So, feel free to watch it at 2x speed. Um, just, yeah, enjoy. Okay, so let's start a little bit with what is our broad perspective. Where are we today in the scope of things, and how did we get here in terms of quantum computing? So, what is quantum computing? Well, before you start saying what is quantum computing, we first really have to say what is classical computing. And classical computing really, it is the manipulation, the information processing of classical information based on Newtonian physics. Now, what we most commonly think about, and which is like a very good facsimile to think about in general, is that computation is done with bits, which are either one or zero. And there's a couple different ways you could think of this. Think of this state of system being represented by, say, a sequence of coins that are either heads or tails. Or, what is actually being done in most of your computers is the state of the system is being expressed via extremely long, like petabytes worth of transistors that are either on or off. And the manipulation of information is done by a sequence of rules. You say if bit 10 is equal to 0, then you flip bit 7, et cetera, et cetera. We manipulate the information, and at the end of the day, we interpret that final information as the output value. And that is computation. It's the transformation of information through these simple rules. And fundamentally, we're thinking of this information as classical, meaning it's represented by these bits. Okay, so what is quantum computation then? Well, let's just put the word quantum in there, and it's information processing, but it's no longer based on Newtonian mechanics, it's based on quantum mechanics. What is quantum mechanics? It's well-established theory that describes nature at the most fundamental level. And where this is good, it's been very useful for describing the behavior of very small or very cold systems. So think of them like a hydrogen atom, where you might remember from chemistry that there are these fixed orbitals, and that the state of the hydrogen atom can be what's called a superposition of these orbitals, or phenomenon like superconductivity. These are all examples of quantum mechanics. Okay, so what is so hard about quantum mechanics? Why do we have to study it differently than we study classical mechanics? Well, despite our best attempts at trying to do anything better, classical computers predicting the behavior of quantum systems of n particles seem to take exponential of n resources to do so, whether that be time resource, space resources, or both. And inherently, this is because we believe that the best way to describe a system of n particles is by a quantum state, which requires thinking about 2 to the n, at least 2 to the n complex numbers in the case that these particles are, what are called 2-bit particles, 2-state particles. But that inherently yields a problem, which is that, the number of known particles in the universe, it's like upper bounded by something like 2 to the 250. So if we wanted to simulate even a 300 particle system, we just simply don't have the resources to do so, right? The space complexity in itself to simulate 300 particles behaving in a quantum mechanical way is larger than the size of our universe. So how could we even classically do anything about it? So another way of saying that is, if nature was classical, behind the scenes, there's a part of the world which we observe, part of the universe we observe, and there's maybe something behind the scenes, something we cannot tell. And whatever's happening behind the scenes is pretty complicated, because these computations that it's corresponding to, as far as we know, are exponential in complexity. But on the other hand, the classical systems that we have, we believe the Church-Turing thesis tells us that these classical systems, if they are of n particles and we want to simulate them for time t, we can do this in time that only scales polynomially in both n and t. So the simulation of classical systems can be done by other classical systems efficiently. Now, this may sound a little bit tautological, but it is a fundamental aspect that is worth understanding. So then what are they up to in the physics department, those who study quantum mechanics? Well, they're doing many things. The first one is they found many ingenious ways of speeding up or approximating these calculations. So while they may be exponential time, 1.1 to the n is a lot faster than 2 to the n, even if they're both exponential. And this has been, and to speed up or finding better ways of representing quantum information, there's a lot of different ways to think about it. There's tools like Feynman diagrams, perturbation theory, mean field approximations, etc. We won't get into that further. They're also developing better computer simulations, whether that be, something like quantum Markov chain Monte Carlo methods, or just better computational tools to connect computation, classical computation, and quantum physics. And thirdly, which is quite important, is they're identifying the regimes of physics where quantum mechanics yields classical approximations. So while quantum mechanics may not be classically simulable always, there are lots of situations where we don't need to think about quantum mechanics. When you're driving your car down the street or you're an engineer simulating a car collision, you're not really thinking about quantum mechanical effects. Those aren't the large order effects, right? In the large and warm scale, our classical approximations to the world seem to do really well. Another place where quantum mechanics can be approximated classically is systems which have perhaps only weakly interacting particles. So the interactions that are quantum mechanical are very small. So classical approximations can be easily derived. But it still begs the question, is there a general theory for simulating quantum mechanics? And many problems we want to study, they seem to do have these elegant solutions in the aforementioned slide that avoid needing these exponential resources. But a fundamental open question is whether all problems have such a shortcut that circumvents the complexity. Okay, so this brings us to history. And the setting is May 1981 in a little house called the Endicott House in, I believe the town is Dedham, Massachusetts, outside of MIT. And this is the meeting of the first annual Physics of Computation conference. And a lot of the people in this photograph actually ended up being big pioneers in the field, and many of the names we'll hear during this course will the faces appear in this photo, including somewhere in there is Richard Feynman, famous physicist. I think he's in the back row, maybe third from the left. I cannot tell. It's a little hard for me to see. But Richard Feynman at this Endicott House 50-person conference, he gives the keynote lecture called Simulating Physics with Computers. Now, this is actually, I think, just very funny, which is the conference is called Physics of Computation, but what Feynman's going to talk about is called Simulating Physics with Computers. So he's sort of turned it on its head. Okay, but what did he say in this fundamental keynote lecture? Well, he postulated two things. He postulated one, that probabilistic computers cannot simulate quantum mechanics, that they just inherently lack the complexity to do so. And the second was, he said, if there was any simulation of quantum mechanics, it must be quantum mechanical in nature, i.e., he was describing the quantum computer. There's a famous quote, which, it's almost criminal not to put up on your slide, which is, he says, the naturist and classical, damn it. And if you want to make a simulation of nature, you better make it quantum mechanical. By golly, it's a wonderful problem because it doesn't look so easy. And this really kickstarted this idea of quantum computation. Can we simulate quantum mechanics with a very controlled quantum mechanical simulator? And this is what Feynman was fundamentally interested in. He was interested in this question of quantum computers for simulating quantum mechanics. But others who were at that conference were listening and they were already thinking ahead. So David Deutsch, he formulates the notion of a quantum Turing machine in 85. So 81, Endicott lecture, 85, David Deutsch formulates quantum Turing machine. 1984, a year before, but temporally, a lot of these things were happening sort of at the same time. Bennett and Broussard, in fact, Charlie Bennett is the person who took that photo, the Endicott photo. They started to think about quantum mechanics for cryptography, and we'll talk about their result in our class later. And in 1993, Ethan Bernstein, Umesh Vazirani, they give the first quantum algorithm demonstrating speedups over classical algorithms. Now, it's important to note, I guess, historically, that Feynman passes away in 1988. So he sees the first two results, but he didn't see the quantum algorithms demonstrating speedups over classical. But which is kind of astounding because Feynman's initial goal was just simulating quantum mechanics. And now here, Bernstein and Vazirani show that past that, their quantum computation can do things that is more powerful. And the problem they're going to talk about a classical problem. I'm going to show quantum algorithms provide an advantage in this setting. Okay, we'll see all these in the course in due time. This is just the broad perspective. Simon in 1994, he will improve the Bernstein and Vazirani result, and he'll give an exponential quantum speedup for a specific problem. He'll show there's a specific problem for which there's an exponential quantum speedup. And then Peter Shor in 1995, well, this deserves its own slide, but he will take the ideas of Simon, Bernstein, and Vazirani and take them to a whole other level and develop the algorithm for factoring. So Bernstein and Vazirani, what they've shown was they've shown speedups, but those were in what is called the oracle model, which we'll talk more about in the class, but right now it suffices to think of the oracle model more as a thought experiment. It's not a real demonstration of speed up. It's more of like in a hypothetical world, in a simplified model, there is a speed up. But what Peter Shor shows is no oracles necessary. Factoring, the problem of factoring integers, that's something you can compute on a quantum computer. And why is this so important? Well, factoring integers is strongly believed to be a hard problem for classical computers. In fact, it's so strong that the modern cryptographic tool, which is used almost everywhere, and has won so many accolades, that is the Revesh Shamir Adelman RSA cryptography. It's fundamentally based on the assumption that factoring integers is hard. So much so that if factoring integers was easy, then RSA cryptography would be broken. And this is the modern cryptographic tool that governs just about everything. Although, okay, we are slowly transitioning away from RSA, but that's a process that's actually been taking a long time. But okay, just because someone based cryptography on it doesn't mean it's hard. Well, because we base so much cryptography on it, people have studied this problem to death, and so many have tried and failed to create an algorithm for factoring that it's sort of something we strongly believe doesn't have a classical algorithm, although we do not have a formal proof to show it. Okay, but what does Shor's algorithm for quantum algorithm for factoring give us? Well, it gives us sort of a reckoning, right? Because it says if you can manipulate quantum information, then we can efficiently factor integers. It's just a theoretical argument saying if these axioms are true, then here's a technique for factoring integers. So what it does is it places us in three worlds. The first world is that quantum mechanics is wrong. It was a good theory while it lasted, but it doesn't describe the world at large scales. Somewhere at some size, maybe n is like we haven't really tested quantum mechanics past, say, 30, 40 particles. I don't know what the exact number is, but after that it breaks down. So you can use it to factor small numbers, but large numbers, it's useless. Like, it's going to fail. And moreover, maybe factoring is probably still hard. The second option is, okay, that's cool and all, but we just haven't found the classical algorithm for factoring, but it exists. So your quantum computer is solving factoring, but it's only doing it maybe polynomially faster than the classical algorithm. There's some classical algorithm out there, maybe it takes n to the 20 time, and we just haven't figured it out yet. And Shor's n to the 3 time algorithm for factoring, it's a whole lot better than it, but it's only polynomially better. Or third, and this is the scenario that we sort of now believe is the correct answer, is that quantum mechanics is true, and quantum computers are provably more powerful than classical computers. There are problems which you can solve on a quantum computer that you simply cannot solve with classical computers efficiently. There is a fundamental difference in the computational technology and what problems they can solve. So, which world do you believe we live in? And moreover, how could you prove that you live in this world? These are actually, well, I won't be able to answer what world you believe in. But we will in this course talk about how you could prove which of the three worlds you're in and how can you gain more and more evidence that you're in one versus the other. Okay. Fast forward to today, what's the situation? Well, the quantum computing industry today is in huge swing. There are tons of companies working on trying to develop a full fledged what's called scalable quantum computer, meaning that it's not a quantum computer for just 5 qubits, 10 qubits, 100 qubits. We have a technique for building a larger and larger computer for the size we want. In the same way that we have a technique for building larger and larger classical computers, we could just keep stacking the computers one after another, and we have a larger computer because we can communicate between them. Right? And what's going on right now on the engineering side is we're trying to solve fundamental engineering challenges to make quantum computers a reality. Um, and moreover, we want to also do in such a way that we are able to solve problems significantly faster than classical computers. So the bad side would be that we build quantum computers and they can do a lot of things, but everything they can do, we can also do classically, right? We really want quantum computers that can do things which they can't do classically. So, for example, we would love it if our quantum computers could solve factoring. But as we'll talk about in a bit, our quantum computers today cannot solve factoring because they still are not able to succumb over noise. So what is that? We sit in this sort of murky middle zone between classically simulable and truly quantum. And that's because we have systems that are big enough, they're like 50 to say 1,000 qubits, that for which classical simulation seems challenging. We don't exactly have algorithms that do so, although we are getting better. People have been writing better and better classical algorithms for simulating these quantum computers. But the other problem is that the quantum computers are still succumbing to a lot of noise. Inherently, just as there's noise in classical computation, there is a notion of quantum noise that is pervasive in computation, and it destroys the information being held while the computation is going on. And when there's too much noise, the computation fails, and then it just succumbs to the noise. So that's the reason why we still don't have large factoring, is because we can't build a quantum computer large enough that can hold the quantum state for long enough such that factoring can be done on this computer. But we're getting better, and we hope to do it soon. Who knows what soon means? It does leave a question, which is, are there still hard problems that you can solve today with quantum computers? And a lot of research is being pushed into this. You'll find lots of papers today about quantum compute that might be titled something like quantum computation before fault tolerance, which is basically what can we do with our quantum computers today before we can handle the noise and handle the error through what is called error correction. There's sort of a little bit of a race going on here, and it's up to us to pick the right horse. And that's because just as there are many technologies for implementing classical computation, transistors, DNA, mechanical computers, analog computers, classically it seems like transistors have really kind of won the race. But people still study the other ones because there are esoteric uses where they do provide power. There are many technologies for implementing quantum computation, some which you may have heard of are like superconducting qubits, ion traps, photonics, topological qubits, etc. And the fun side is that we don't actually know which of the technologies will prevail, which one will do the best. And different companies and research groups are trying out different techniques, and new techniques are being developed every day. It's a very nascent field in this aspect. And so there's a fun question of, who will be the first to build a quantum computer? Which type of quantum computer will be the one that is pervasive? And I'll say this, that in my opinion, we're going to see many technologies work in parallel, because what we'll find is actually that the quantum computers can be highly tuned to the technology underhand, and certain problems can be solved much, much faster on one technology versus the other. But anyways, that's on the experimental side. What's going on in theory? Well, in theory land, we are developing new quantum algorithms for interesting problems, but we're also improving the old quantum algorithms, the ones that we showed in the history slide, to be less bulky, to be able to run faster on these smaller computers, because we're sort of handling software meets hardware. It is in a funny world where like our software is way, way better than the hardware that we could work on. And to that effect, we are studying what's called error correction. And this is sort of produce software solutions to handle the noise that's inherent in the hardware. Something that I do personally is I study quantum complexity theory, and that's to identify the problems for which we do not believe there are efficient quantum algorithms. We show where the boundary of quantum computation sort of touches the boundary of classical computation, where these speedups are either unlikely or just minimal. Um, and another fun area is that we've been thinking about quantum computation as a lens, or maybe the right word is a tool in other areas. So there's been a lot of work recently on connections between cosmology and quantum computation. How do we describe phenomena such as black holes through computation? There's a famous paradox called the black hole firewall paradox. What does that mean? Is there a way to understand it through the lens of computation? And well, it's about a large quantum object, so the right lens is a quantum computational lens to study it. We've also been thinking a lot about cryptography, both preparing cryptography for inevitable quantum computers so our crypto systems don't get broken, and to also use quantum computers to enhance cryptography, to build technology that provably couldn't exist with just classical cryptography, but quantum cryptography now makes it available. Okay, a few administrative notes before we talk a little bit about what's exactly in this course. Actually, let's go straight into the course. So what is this course? This course is an implementation agnostic course, meaning that I'm not going to talk about superconducting qubits, ion traps, etc. Instead, the way it'll kind of work is in our first lecture, we will discuss some axioms and theory of quantum computation. And then we will derive from these axioms in a completely rigorous mathematical formalism a lot of technology. So we'll derive algorithms, we'll derive a model for what quantum computation could look like, what are problems we could theoretically solve, etc. But we'll do this in implementation agnostic, so that anything we say can be translated to any different implementation, as long as in that implementation you can implement the core axioms. You will learn fundamental algorithms and protocols. All the algorithms that I previously discussed are all elements of this course. I hope you'll get a picture of what is being studied today on both the theory and practice side. Your picture will be a little bit more theory heavy, but there are many courses both at UW and online to learn what is going on in practical and experimental quantum computation. And I hope you'll try to get an understanding of the big open questions as well. Not only what has been studied and our techniques, but also where our knowledge is lacking and where we believe the frontier of quantum computation sits. Okay, but what will you not learn? Unfortunately, you will not learn how to build a quantum computer, and that's mostly because I have no idea. I myself am a theoretical computer scientist who knows a little bit about quantum mechanics, just a minute amount. And I have no idea what the implementations look like exactly. So if you learn something, please let me know. You will not learn how to use a quantum computer or how to build a quantum computer to mine Bitcoin faster than anyone else. Sorry, the theory and practice here just are a little bit too far apart. You will also not learn quantum mechanics. You know, um, quantum computation is a really nice perspective with which to start to understand quantum mechanics. And I learned quantum computation first and then quantum mechanics afterwards. But um, we will not describe all the complexity of quantum mechanics. We'll work with a very simplified approach. We'll only do with like finite dimensional vector spaces, etc. Um, what we'll do is we'll sort of derive what we call the axioms of quantum computation, not the axioms of quantum mechanics, and derive all the results from these. These will be like a subset of the axioms of quantum mechanics in our very simplified model. What you will learn is the beautiful theory of quantum information and computation, something that really excites me fundamentally. Okay, Now kind of a little bit more administrative stuff. So I didn't set any prerequisites for this course because I want this to be open to people who come from many different backgrounds, and maybe you know things about one area and you don't know a little about another, and you can sort of play catch up as necessary. What will be required will be sort of a strong mathematical background. I'll say more on the next slide about that. Um, but it is possible that the mathematical rigor of this course is above that of students. And that's okay. It just means you have to study a bit more math, either on the side or come back to this course afterwards. Okay, the biggest requirement is an understanding of linear algebra. Everything we're going to do is going to be thought about in terms of vector manipulations, matrices, operators, etc. And there will be a lot of linear algebra. Being comfortable manipulating vectors in high dimensions is sort of a necessary prerequisite for this course. In addition, sort of basic mathematical tools used to bound limits, etc., such as like Chernoff bounds, Markov inequality. These kind of tools will just be assumed in this course. If you don't know them when they come up, you can ask the TA about it, or you might have to read a little bit on the side in addition. So just being very comfortable with a lot of math never hurts, and this course is no exception. So to that effect, this course will be about taking classical computation and lifting it to quantum computation. So exposure to theory of computation courses. Here listed are some of the undergraduate and graduate courses, which should include all the necessary like linear algebra and mathematical tools needed, is a very good idea. Knowing a little bit about algorithms is helpful, a little bit less important than actually the mathematical tools, because the quantum algorithms sort of go a little bit helter-skelter around classical algorithms, but it never hurts to know more about how things work classically so that we can compare and contrast the two effectively. On the other hand, while math and CS requirements are strong, physics, I'm almost going to require no physics, because all the things we're going to derive are based on these purported axioms of quantum computation that we will discuss in the first lecture. So it doesn't hurt to have taken a previous course in quantum mechanics and sort of know the intuition behind them. All of that can be understood through through just this course. So no quantum mechanical requisites are necessary. On the website, I list a little bit about analysis and group theory, which are helpful to understand these things, but I don't think you'll need them in any depth, and I won't be assuming any knowledge of those. Okay, to that effect, I've put up a problem set. I call it problem set 0. It's completely optional. It's not graded. The solutions are already posted, and it's available on the course website. The use case of this is for you to peruse and make sure you can solve the problems with little difficulty. It's sort of considered a litmus test to decide if this course is right for you, either you are ready to jump into this course. If it's hard, that's okay, but that just means that you might need more math review before the course starts. Or the other suggestion is you can take the undergraduate version of this course, which is a little mathematically lighter, will slow things down. I'll explain more of the math required during that course. And keep in mind that CSE 534 is now planned to be a routine course taught at UW in the CS department. So even if you're not able to take it this year, it's perfectly all right to come back next year.